You probably think you understand gravity. You step onto a scale, watch the numbers settle, and assume that what you are seeing is your weight, the result of Earth pulling you downward. It feels natural to describe it that way. You drop your keys and they fall. The moon circles the Earth and the planets orbit the sun. Everything seems to follow a clear and simple rule. Objects with mass attract each other. This picture, first described by Isaac Newton, has shaped how we think about gravity for centuries. It feels neat, logical, and complete, but the surprising truth is that this explanation, while useful, is not fundamentally correct. When you examine gravity more deeply, you discover that it is not actually a force in the way we usually imagine. It is not like a rope pulling you down or a magnet dragging objects together. That familiar image is only an approximation, a simplified way of describing something far more complex. To really understand gravity, you have to abandon the idea of a pulling force and begin to see the universe in a completely different way. Before diving into abstract theory, try a simple experiment. Stand up and pay close attention to how your body feels. Focus on the sensation of your own weight. You might instinctively say that you feel gravity pulling you toward the ground. But if you analyze your actual experience, something interesting appears. The feeling you notice is not a pull downward. Instead, it is a pressure pushing upward on the soles of your feet. The floor is pressing against you. That is the only physical sensation you directly experience. This is a crucial point. You never actually feel gravity itself. You do not feel a force dragging you toward the center of the Earth. What you feel is the ground resisting your motion. If the floor suddenly disappeared, you would not feel a pull downward. You would feel weightless as you began to fall. That is a strange and counterintuitive idea, but it reveals something important about how gravity really works. The deeper explanation comes from the work of Albert Einstein. He showed that gravity is not a force at all, but a consequence of the geometry of space-time. Massive objects like Earth bend the fabric of space-time around them. Instead of being pulled by a force, objects simply follow the natural paths within this curved geometry. When you stand on the ground, your body is actually trying to move along one of these natural paths, but the ground prevents you from doing so. The resistance you feel is the surface pushing back, stopping your motion through curved space-time. In this view, falling is not caused by a force pulling you down. Falling is what happens when nothing is stopping you. An object in free fall is actually following its natural path, moving as it wants to move according to the shape of space-time. That is why astronauts in orbit feel weightless. They are constantly falling, but they never hit the ground because they are moving sideways fast enough to keep missing it. Once you begin to see gravity in this way, your entire perspective shifts. The universe is no longer a place where invisible forces reach out and pull things together. Instead, it becomes a dynamic structure where space and time themselves are curved and shaped by matter and energy. Objects move not because they are pulled, but because they are following the geometry of the cosmos. This realization is both unsettling and beautiful. What seemed simple at first, a force pulling you downward, turns out to be a deep property of reality itself. And when you truly understand it, the universe no longer looks like a collection of objects interacting through forces. It looks like a vast, curved stage where everything moves according to the shape of space-time. It is always a push, never a pull. So if you can't feel the pull, where is it? Here is something even stranger to consider. The moon is currently falling toward the Earth. It has been falling for billions of years, plummeting through the vacuum, yet it never gets any closer. It just circles us endlessly. It is a fall that never lands. What kind of pull behaves like that? A force that tugs forever but never manages to reel the object in. Furthermore, according to Isaac Newton, this pull happens instantaneously. If you were to magically pluck the Earth out of existence, Newton's theory says the moon would feel the loss of gravity instantly across 240,000 men-years of empty void. How? What carrier pigeon delivers the message? What is the mechanism? Newton himself was deeply troubled by this. He couldn't explain it. He referred to it as action at a distance. And in his private letters, He admitted that the idea of one body affecting another through a vacuum without anything else to transmit the force was an absurdity. He didn't understand how it worked. However, his mathematics were gorgeous. His predictions were flawless. Because the math worked, people stopped asking the uncomfortable questions about the how. They shouldn't have stopped asking to understand where the mistake happened. We have to travel back several centuries. Before Newton, nobody truly understood how the planets moved. Copernicus had the bold idea that they orbited the sun, which was a great start, but how? What specific paths did they trace? Enter Tycho Brahe. He wasn't just an astronomer, he was a data obsessionist. He built a massive observatory and spent decades recording the positions of the planets night after arduous night. Year after year, he measured angles with giant brass instruments, achieving precision down to tiny fractions of a degree. Why go to such lengths? Because Tycho knew that you cannot understand nature by guessing. You have to look. You have to measure with extreme care. You must write down exactly what you see, not what you want to see. That is where real science is born. His mountains of data eventually reached the hands of Johannes Kepler. Kepler was determined to unlock the secret shape of planetary orbits. He started with the assumption that they were circles, the most perfect shape. When he ran the numbers, the predictions were incredibly close to the observations, but they weren't perfect. The orbit of Mars was off by a mere 8 arc minutes. That is 860ths of a single degree. Most people, almost anyone else in history, would have shrugged that off as a measurement error, a smudge on the lens, a slip of the hand. But Kepler knew Tycho Brahe. He knew that man did not make 8 arc-minute errors. He trusted the data more than his own theory. So Kepler threw out the circle. He threw out his theory and started from scratch. After years of agonizing calculation, he found the answer. Ellipses. The planets move in stretched out circles or ellipses with the sun sitting at one of the focal points. It was a perfect match to the data. It was beautiful, but it raised an even bigger, more haunting question. Why ellipses? Why that specific shape? While Kepler was gazing at the heavens, Galileo Galilei was down on Earth doing something that seemed much simpler. He was rolling balls down ramps. It sounds trivial, almost like child's play, but watch closely. When you roll a ball down a slope, it speeds up. When you let it roll onto a flat surface, it keeps going. It doesn't stop immediately. Now engage your imagination. Imagine you could eliminate all friction, no air resistance, no roughness on the floor. What would happen? The ball would roll forever. It would maintain the same speed and the same direction for eternity. This idea deeply bothered people at the time. Intuition tells us that motion requires a continuous push and that things naturally want to come to a rest. Galileo proved that intuition is backwards. Motion is the natural state. An object moving in a straight line at a constant speed needs no explanation. That is the default setting of the universe. What requires an explanation is change. If something slows down, that's friction. If something speeds up, that's a push. If something changes direction, that is a sideways force. This is the concept of inertia, the first law of motion, and it creates a massive puzzle for astronomy. If the natural state of an object is to move in a straight line, then planets should be flying off into deep space in straight lines, but they don't. They curve. Their paths bend continuously toward the sun. Something must be deflecting them at every single instant. Isaac Newton saw this clearer than anyone. Planets want to go straight. That is their inertia, but they curve. Therefore, something is changing their motion constantly. He named this influence gravity. He proposed the universal attraction between any two masses. The force depends on mass and distance. More mass equals a stronger pull. Greater distance equals a weaker pull. Specifically, the force drops off with the square of the distance. With this single principle, everything clicked into place. Why ellipses? Because planets are trying to fly past the sun, inertia, while simultaneously falling toward it, gravity. The combination of this sideways motion and inward pull creates the elliptical path. Kepler's laws weren't just observations anymore. They emerged naturally from Newton's math. Why does the moon orbit the Earth? It is the same principle. The moon is falling toward the Earth, but it is moving sideways fast enough to keep missing us. It is falling around the Earth instead of into it. Why does an apple fall from a tree? The Earth attracts it. It is the same force, the same law, just on a different scale. Newton performed the beautiful calculation to prove this. He figured out how far the moon falls away from a straight line path every second. Then he calculated how fast objects fall here on Earth's surface. When he accounted for the distance difference, the numbers matched perfectly. This was revolutionary. It meant that the force pulling an apple to the grass is the exact same force holding the moon in the sky. Heaven and earth were no longer separate realms. They were ruled by the same physics. With Newton's law, the universe made sense. Ocean tides happen because the moon pulls on the Earth's oceans. The Earth is round but bulges at the equator because it spins. Comets return on predictable schedules because they are locked in elliptical orbits. Even strange anomalies found explanations. For instance, Jupiter's moons sometimes appeared ahead of schedule and sometimes behind. It turned out that light takes time to travel. When Earth was farther from Jupiter, the image of the moons took longer to reach us. This led to the first calculation of the speed of light. When planets wobbled slightly in their orbits, astronomers realized they were pulling on each other, not just reacting to the sun. By analyzing the wobbles in Uranus's orbit, mathematicians predicted there must be another planet out there. They pointed their telescopes where the math told them to look. And there it was, Neptune. For 200 years, Newton's law of gravity stood as the ultimate achievement in science. It explained everything anyone could measure. It was the bedrock of physics. But there was one tiny detail, one nagging thread that if pulled would unravel the whole tapestry. Drop a hammer and a feather in a vacuum. They hit the ground at the exact same time, perfectly together. Think about what that means. The hammer has much more mass than the feather. According to Newton, gravity pulls on the hammer much harder. It should be ripped down to the floor with far more force. However, the hammer also has more inertia. It is harder to get moving. It resists acceleration much more than the feather does. In Newton's view, these two effects, the stronger pull and the stronger resistance, cancel each other out, not just roughly, but perfectly. Every object, regardless of what it is made of, falls at the exact same rate. Why? If you are enjoying this deep dive into the mysteries of the cosmos, take a second to hit the like button and share this with a friend who loves science. It helps Feynman analysis grow and keep bringing you these stories. Now back to the problem. Newton's theory requires mass to have two totally different properties. First, there is gravitational mass, which determines how strongly objects attract each other. Second, there is inertial mass, which determines how hard it is to accelerate an object. For some reason, these two distinct properties are always perfectly proportional for every substance ever tested, down to incredible precision. But why? Why should the attracting property of an object be exactly equal to its resistance to movement property? Newton had no answer. He just accepted it as a remarkable coincidence that made the mathematics work. But was it a coincidence? Decades later, Albert Einstein asked a different question. What if this equality isn't a fluke? What if this perfect synchronization is telling us something fundamental about what gravity actually is? He devised a thought experiment. Imagine you are in a closed room with no windows. You feel your normal weight pressing your feet to the floor. Now I ask you, are you sitting in a room on Earth or are you in a rocket ship in deep space accelerating upward at 9.8 ms squared? Can you tell the difference? If you drop a set of keys, they fall to the floor in both cases. If you throw a ball horizontally, it follows a curved path to the ground in both cases. If you stand on a scale, it reads the same number. There is no experiment you can perform inside that room to distinguish gravity from acceleration. This is known as the equivalence principle. Einstein realized that if you truly cannot tell the difference between gravity and acceleration, maybe it's because they are the same thing. Maybe what we call sitting still in a gravitational field is actually a form of acceleration. This triggered Einstein's revolution. Consider objects in free fall. An apple falling from a tree, the moon orbiting the Earth, an astronaut floating in the ISS. None of them feel any force. If you cut the cables of an elevator, the people inside float. They become weightless. They are moving naturally, following their natural paths. No forces, no pulls, nothing acting on them. But wait, the apple is clearly falling. It appears to be accelerating toward the ground. How can it have no force acting on it? Einstein's insight was profound. What if the apple isn't accelerating? What if the apple is following the straightest possible line, but space itself is curved? This is the heart of general relativity. Gravity is not a force that reaches out across empty space. Gravity is the curvature of space and time. Massive objects do not pull on other objects. Instead, they warp the fabric of the universe around them. They bend it, curve it, and distort the geometry. The apple isn't being pulled down to the grass. It is following the straightest possible path through a curved space-time. However, near the Earth, space-time is curved in such a way that straight ahead points toward the center of the planet. Now look at yourself again. You standing on the ground are not being pulled down. You are trying to follow your natural path through curved space-time. A path that leads to the center of the Earth, but the ground is in your way. The floor pushes you upward, preventing you from following that natural trajectory. That sensation of weight, that isn't gravity pulling you down. That is the ground pushing you up, accelerating you off your natural path. You are being constantly deflected from your destiny. Einstein made a concrete prediction to prove this wild idea. If gravity is really just curved space-time, then light itself should be affected. Light has no mass. In Newton's theory, gravity shouldn't touch it. But if space itself is curved, then a beam of light trying to go straight must follow the curve. It should bend. During a total solar eclipse in 1919, astronomers measured the positions of stars located near the sun's edge. The stars appeared displaced from their true positions. The starlight had bent as it passed through the curved space around the sun, exactly as Einstein had predicted. This is gravitational lensing. We see it in our telescopes today. Snorts. Massive galaxy clusters bend the light from objects behind them, creating distorted arcs and rings. It is direct visual evidence that space itself is malleable. Think about astronauts in orbit. They look weightless floating around the cabin. We often say there is zero gravity up there. That is completely wrong. The gravitational field at the altitude of the space station is about 90% as strong as it is here on the surface. If gravity were turned off, they would fly away into deep space. So why do they float? Because they are falling. The station, the astronauts, the air inside, it is all falling toward Earth constantly. But like the moon, they are moving sideways at 17,000 nanometersmo. As they fall, the curve of the Earth falls away beneath them at the same rate. They are in a state of perpetual freefall. Since everything is falling together, there is no sensation of weight. It feels exactly like floating in empty space, because physically the two states are identical. In freefall, you are surrendering to the geometry of the universe. This geometry explains everything. Why is the Earth round? Not because a force crushed it into a ball, but because space-time curves equally in all directions around the center of mass. Matter simply settles into the shape dictated by that curvature. A sphere is the only shape where every point on the surface is equidistant from the center of the warp. We have to remember it isn't just space that curves, it is time as well. We live in a four-dimensional fabric called space-time. Massive objects create depressions or wells in this fabric. The sun creates a deep well. The Earth creates a smaller one. Even you create a tiny dimple in space-time. Objects moving near these wells follow the curvature. The moon doesn't orbit because of a tether. It orbits because the straightest line it can travel in this curved environment happens to be a circle. When you throw a ball, it traces an arc. To you, it looks like a curve. But in the 4D geometry of space-time, that ball is taking the straightest possible route. It is us standing on the ground who are following the unnatural curved path through time by refusing to fall. In Newton's picture, you are static, held by balanced forces. In Einstein's picture, you are accelerating. You are like a person standing in a rocket ship that is blasting upward. The floor hits your feet, continuously pushing you away from the natural path of free fall. This is why when you trip and fall, you feel a sudden rush of relief, physics-wise at least. For that brief second before you hit the ground, you are free. You are no longer being accelerated. You are finally doing what the universe wants you to do. Once you grasp that gravity is geometry, the most extreme phenomena in the universe begin to make sense. Consider a star. A star is essentially an enormous sphere of gas held together by its own gravity, which shapes the surrounding space-time into a deep curvature. Naturally, everything within that star tends to move inward along those curved paths, meaning the star is constantly on the verge of collapsing under its own weight. What prevents this collapse is the intense outward pressure generated by nuclear fusion at its core. In this process, lighter elements fuse into heavier ones, releasing tremendous energy that pushes outward against gravity. For most of a star's life, there is a delicate balance between this inward pull and outward pressure, keeping the star stable. However, this balance cannot last forever. Eventually, the star begins to run out of fuel for nuclear fusion. As the energy production decreases, the outward pressure weakens. Once this pressure drops below a critical level, gravity takes over completely. The star can no longer support itself, and it begins to collapse inward. This collapse can happen extremely rapidly, and the consequences depend on how massive the star is. If the star is large, but not too extreme, the collapse compresses matter to astonishing densities. Atoms are crushed so tightly that electrons are forced into protons, forming neutrons. The result is a neutron star, an object incredibly small compared to its original size, but unimaginably dense. A neutron star can be about the size of a city, yet contain more mass than the sun. Just a teaspoon of its material would weigh billions of tons on Earth, demonstrating the extraordinary compression taking place. But if the star is even more massive, the collapse does not stop at the neutron stage. In these cases, not even neutron pressure can resist the force of gravity. The curvature of space-time becomes so extreme that every possible path within it points inward. There is no direction that leads outward anymore. Even light, which travels at the fastest possible speed, cannot escape. This is what we call a black hole, a region where the structure of space-time itself forms a one-way trap. Near a black hole, the geometry of space and time becomes so distorted that it dramatically affects everything nearby. Matter that falls toward it heats up and emits powerful radiation as it spirals inward, creating bright and chaotic regions around the invisible center. Although we cannot see the black hole itself, we observe its presence through these violent effects. At a certain boundary, known as the event horizon, anything that crosses it can never return. Beyond this point, all paths lead deeper inward. All of these phenomena, from stars to black holes, arise from a single underlying principle. Mass changes the shape of space-time, and objects move according to that shape. This idea, introduced by Albert Einstein, reshaped our understanding of gravity. It explains not only the motion of stars and galaxies, but also everyday effects like falling objects and ocean tides. Even subtle phenomena, such as the bending of light around massive bodies and the ripples known as gravitational waves, are consequences of this same principle. The earlier description of gravity, developed by Isaac Newton, is still extremely useful. It allows us to calculate motion, build structures, and navigate space with great accuracy. However, it is ultimately an approximation. Einstein's perspective reveals the deeper truth. Gravity is not a force acting at a distance, but the result of curved space-time guiding the motion of matter. This concept is beautifully summarized by physicist John Archibald Wheeler, who said that space-time tells matter how to move, and matter tells space-time how to curve. This interplay defines the structure of the universe itself. When you stand on the ground, you are not being pulled downward. Instead, the ground is pushing you upward, preventing you from following your natural path through curved space-time. So the next time you see an object fall, think of it not as being pulled by an invisible force, but as finally being free to follow the geometry shaped by mass. Gravity, in this deeper sense, is not a mysterious attraction. It is the shape of reality itself, guiding everything from the smallest falling stone to the largest structures in the cosmos.